Yes, class. Good evening. Priya, Reem, Rifat, and Wafia.
Good evening, ma'am.
Okay, class. So refractive index was completed. Now we'll start with a new topic, apparent depth. Now understand what is meaning of apparent depth. Apparent depth basically means what is actually not the depth that is you are able to view, which you are not able to view. For example, if there's a glass of water, and in the glass of water, if I keep a coin, let's say if I keep a coin over here, this is the coin. What will happen at a certain angle? If you'll see, for example, this is the glass. At this certain angle, if you will view it, the coin will appear to you at a higher distance. The height will be lesser from the above water's air interface. When you will view it, when you will actually touch the coin will you will feel that the coin is actually present at the bottom. But if you will see it by your vision, you will be able to notice that coin is actually present right away, above, just above to what its actual depth. So that depth that is not actually present, but you are able to observe just because of the refraction that occurs because of the two different media, air, water, air, any liquid. That is known as apparent depth. And real depth means what is actual depth. For example, if coin is there, let's say this is D real, this is D real, D2, let's say, D1, let's say, D1. D1 is the real depth of it. Fine, this is the real depth of it. Now what will happen? See, this interface is there. This interface is there. Now see, what will happen? Rays will be incident. So see, water is the denser medium, air is the rarer medium. Now object is where? Object is located in the denser medium, right? From the object is located here. So now the rays will be incident at this surface. Rays will be incident at this surface. Just a second. Now see, at this surface, the normal will be drawn. And see, since it is moving from denser to the rarer surface, so it will move away from the normal. Fine, let me redraw this. This will be refracted. Now, if you produce it, here you will be able to see the image, right? Now, these rays will enter the human eye. These rays will enter the human eye. This. So if you notice, this was the actual height. Now this becomes from the surface. This is D2, which is the apparent depth. This is what is meant by apparent depth. This coin was actually placed here, but because of refraction and since light travels in a straight line, because of that, this is directly, we are able to view it a little above from the original height that is located. So see, this part, this was angle of incidence, right? This was angle of incidence and this was angle of refraction. If you notice here, since this line and this line, this and the dotted normal, this normal, both are parallel to each other and this acts as a transverse. So this will also be angle I, and because of alternate angles, and this angle is R, so this angle will also be R due to corresponding angles. Look here. This ray normal, this normal is parallel to this ray. Let's say this is some A, this is some O1. Fine. This is some O1. This is the image that has been formed. This angle I and this angle I, both are alternate angles. So these are equal. That's why I've written I. And this angle R and this angle R, Both are what? Both are corresponding angles. That's why both will be equal. Fine. Now see, so this is what? D1 is the real depth, D2 is the apparent depth. Now see, if you look at this triangle that has been formed, O1, AB. Now see, two triangles are formed actually here. This is one triangle that is formed, and this is one more triangle that has been formed. This you have to look here. See, this is point A. This is not point A. Otherwise, this will become confused. Let me name the point. See, this point is A point. Fine. This point I'm marking it as A point. This point I'm marking it as B point. This one I'm taking it as O1. Fine. O1. This is water. Now when I'm talking about O1, AB, this complete big triangle. So sine I will be equal to what? In this bigger triangle, sine I will be equal to perpendicular is AB, right? And hypotenuse is O1B. So sine I will be equal to what? Sine I will be equal to AB divided by O1B. Let's mark this as O2. This image, let's mark this as O2. Now, if you look at this triangle, O2AB, this smaller triangle, if you look at this triangle, this smaller triangle. So here sine R will be equal to what? Again, perpendicular by hypotenuse. So AB by O2B. So sine R will be equal to what? Sine R will be equal to, again, AB by O2B. Fine. Now let's take the ratio. So sine I by sine R, this will be AB by O1B into O2B by AB. AB gets cancelled. We are left with O2B by O1B. O2B by O1B, yes, correct. Now see, these 2 points, no, A and B, these are actually not at this distance. This is a very big distance that I am drawing. This is a very small angle. Very, very small angle. Otherwise, if this was a very large angle that was subtended, then the image would have been formed at a greater depth. All right, or we would have seen the image very superficially on it. But we still see a little depth is possible, a little depth is available. So what happens is that this point A and B are very close to each other, right? This angle of incidence is very small, angle of refraction is very small here. So this A, B, instead of writing everything as O1B and O2B, I can even write it as O1A. B, instead of this B point, I can replace it by A. And why do I need to replace? Because I want to write it in terms of the real depth and the apparent depth. So this is O2B can be written as O2A. O1B can be written as O1A. That is just because of the fact we are using small angle approximation and the fact that both are equal, both are very close to each other. So O1B is approximately equal to O1A and O2B is approximately equal to O2A. Why did we do this? Because we needed O1A and O2A. Right, O1A and O2A was needed, no? Depth, O1B and O2B was what? O1B and O2B had no value, had no significance. Now let's write sine I by sine R. Instead of writing it as O1A or O2, instead of writing it as O1B and O2B, I'm writing directly it as O1A divided by O2A. Since this was obtained, now see what is O1A and what is O2A. See, O1A, this complete is actual depth where the coin was actually placed. So that becomes the real depth. Instead of writing no D1, D2, I'm using DR and DA so that you are able to distinguish. And D2 is the apparent depth, which is not the actual depth, but we are able to observe it. Fine. So O1A is the real depth and O2A is the apparent depth. So sine I by sine R is equal to apparent depth by real depth. Now, Snell's law. Snell's law we did. Refraction when we are doing, we did Snell's law. What was Snell's law? We did no Snell's law. In the last class, we have done no Snell's law. Yes, what was the statement of Snell's law?
The ratio of sine of angle of incidence.
Yes. It's the Snell's law. Snell's law basically deals with, you have Snell's law. Snell's law basically says that sine I by sine R is actually 1 upon the refractive index. Didn't we do the laws of refraction? Yes, class, I'm asking you all. Reflection we had done, the laws of reflection. The refractions did we do or not? Laws of refraction. See, reflection we have done. Refraction I'm asking. This was, here this was about reflection when angle I was equal to angle R. I'm asking about refraction. Did we do or not? Yes or no? Check into your notes. Let me know. I'm asking you all. Laws of refraction. Because Snell's law is included over there only. Okay, we have not done. See, basically in this laws of refraction, no, when you have laws of refraction, in laws of refraction, one statement remains the same. That is incident ray, refracted ray, and the normal all lie in same plane. This remains the same. Fine. This is not reflected ray, this is refracted ray. Second law is basically that ratio of sine of I by sine of R gives you n to 1. That is the refractive index of second medium with respect to the first one. Or you can write it as n2 by n. And this law is known as Snell's law. Fine. Note this down. Note down this law first. Then we'll come back. Or let me explain you that at the end you can write both the things together. So Snell's law says that sine I by sine R is equal to what? It is equal to the refractive index. Now, how to write Snell's law? For example, this is one medium having refractive index n1. Angle formed is I here. Here angle formed is R and here refractive index is n2. Best way to write Snell's law is take the refractive index of the medium, multiply it with the sine of the angle that is present within that medium. Like here I is present, so multiply it with sine I equal to. Here refractive index is n2. Multiply it with this medium, which is angle that is sine R, like this. Any case you have. Or let's take some more case. This is 30 degree. This is, let's say, 20 degrees. Here refractive index is 5. Here refractive index is, let's say, 3. So how will you write Snell's law over here? Refractive index of this material, that is 5, into sine of the angle that is present within that material, that is sine 30, is equal to refractive index of the material along with the angle that is present, that is sine 20. This is how we write Snell's law. So here also, how can we write Snell's law? Here also, if we write, if n is the refractive index of air, let's say liquid of the water. For air, refractive index is 1. All right, for air, refractive index is 1, value of refractive index. I think in the last class, we didn't complete it. No, that's why. I thought we have already completed with these laws of refraction. Here, we have laws of refraction. That's why. Anyways, we'll do it. For refraction, we'll do it. Because one more topic, no, you have compound plate and simple plate. That also we have to do. So that we'll do. Let us complete with apparent depth first. So Snell's law is very important law that will be asked you in the exam. I'll do it again. So here also sin I by sin R will be equal to what? 1 by the refractive index N2 by N1. N2, that is one medium is here, other medium is, let's say, N. N is what? N is the refractive index of liquid. Here it is water, it can be any liquid. So basically, apparent depth is equal to real depth divided by the refractive index. This is actually the formula. Because sin I by sin R is what this is, apparent depth by real depth. So apparent depth by real depth, this is the formula which you get. Fine. This is actually what is the formula of apparent depth. And remember this fact, if your object's radiation, that is the incident rays falling from the denser to rarer, your real depth will be greater. Like in this example, what we did, the light rays were falling from denser to rarer. From water to air, no, the rays were going. Coin was there within water. So from water to air, the rays were going. So didn't you notice real depth was greater and we could see the coin slightly above, means apparent depth was small. But had it been opposite, the object, if the object is some object is kept in a rarer medium and from there light rays are going into the denser medium, then we'll see the object is actually at a shallow distance, but you will see the image formed at a greater depth distance. Because in that case, apparent depth becomes greater than the real depth. Noted till here? If you have any doubts in Snell's law, please let me know, because I thought we have completed it in the last class, but it is left. Laws of refraction we didn't do. No. Some things in refraction are left, like when the rays move away from the normal towards the normal, compound plate, lateral shift, all that is left. That all we'll do. Refraction is a big topic. See class, this difference now that arises before you write this part, one more thing. This difference that is arising, you're seeing. This is the real depth, this is the apparent depth. This difference is there. Do you notice this difference? So this difference that you are able to observe and you notice here, this is actually known as the shift that has occurred in the image. So this is the real depth, this is the apparent depth, and the shift has occurred. This was here was the object, and now here you are able to see the image. So how will you write it? Simply it is the difference between both the depths. So shift is actually the real depth minus the apparent depth. So even if you write the formula of apparent depth from here, so that becomes d real by n. Take d real common, that becomes 1 minus n. So this is the formula of shift. To do add this also into your notes. See the apparent depth of an object at the bottom of tank filled with liquid of refractive index 1.3 is 7.7 centimeters. Means the apparent depth is 7.7 centimeter. Refractive index is 1.3. What is the actual depth means? What is the real depth? So apparent depth is equal to real depth divided by the refractive index. Right. So real depth will be equal to apparent depth multiplied by refractive index. So apparent depth is 7.7, refractive index is 1.3. So this will be around 10.01 centimeter. Someone just cross check whether this multiplication is 10.01. Copy it down. See, the question says a mark is made at the bottom of beaker and a microscope is focused on. Microscope is raised through 1.5 centimeters. You have microscope in your syllabus. The types of microscopes are also there. Compound microscope, simple microscope that you will do. To what height must water be poured into the beaker to bring the mark into focus? So this question is based upon shift. See what happens. What is happening over here? What is it? It says that, and refractive index is also given. Beaker is there. It is filled with water. So a mark is made at the bottom. Let's say here a mark is made. A mark is made at the bottom of a beaker and a microscope is focused on it. Now microscope is raised through 1.5 centimeters. It means here if the mark is made from the microscope, you are able to see it. Now the microscope is raised to focus it where the depth, where the image is now you are able to see the actual image. Got it? This was the real mark that was made. But since when the microscope was focused, at this point when the microscope was focused, at this point, it wasn't visible. So microscope was shifted, it was adjusted for 1.5 centimeter above, and here now a clear image was found. So this was the difference that arise. Can anyone tell me what is this 1.5 centimeters? Real depth, apparent depth, what is this? 1.5 centimeters. This is 1.5 centimeters. What is this 1.5 centimeters? Yes, Priya, right? Any other answer by anyone? It's shift, because this is the apparent depth, this is the real depth. And the difference between real and apparent is the shift. So shift, you have it as 1.5. Refractive index is 4/3. Real depth is not given. No, that is asked. What is the thickness, or to what height must the water be poured into the beaker to bring the mark into focus? It means what is the real depth of this mark? That is unknown. So D real is unknown. I think we need not require anything else. Shift is actually equal D real 1 minus 1 by n. D real you can say, or you can directly use thickness word also. So this is equal to what? 1.5 is equal to 1.5 is equal to thickness, let's write 1 minus 1 by n. So that becomes 4/3. No, 4/3 is n. So that becomes 3/4. It will get reversed. So it will become 3/4. So 1.5 is equal to T. 4 minus 3/4. This is 1. T is equal to 1.4 into 1.5 into 4. That is 6 centimeters. So real depth will be 6 centimeters. So note it down. This completes your apparent depth. I'll now do some of the basics of refraction, how to do the normal, how to draw the normal, that all. But before that, note it down. Doubts you have, let me know. Question. Okay, question. Okay. Oh, fine. I'm not scrolling. Write down the question first. Okay, classes, I was telling about the refraction part, no? How to write it. So, yes, here I'll discuss the laws of refraction. This part was actually, I thought we had covered this, but it was left in this batch. So that's why directly I had started with it. Now, see, refraction, phenomena of change in path of light, as it this we had discussed when we were discussing refractive index, that it is the bending of light, oblique bending of light. And initially also we had discussed that bouncing back of light was reflection, bending of light is refraction, and absorption was also a third phenomena that could occur. All right. Now see, incident ray is there, it gets refracted. The angle of incidence is the angle that is made between the incident ray and normal, and this will remain fixed for reflection or refraction. Refracted ray is the angle of refraction, that is the angle that is formed between the refracted ray and again the normal. Now, laws of refraction. Now you can write it properly from here. See, two laws. First law says that same thing, all lie in the same plane. And now, why does this occur? Why is there a refraction occurring? Light is coming from here also. Why it is not bending somewhere else? Why is it coming straight? Because medium is same. Now, as the medium changes, now speed also changes. So when your speed changes, there is obliquely bending of light because of deviation in the speed. It slows down or it fastens up. That is the cause of refraction. So first law is simple. Incident ray, refracted ray, normal, all lie at the point of incidence. Fine. Snell's law is basically that sine of angle of incidence and the sine of angle of refraction, this remains constant. And that constant term is the refractive index, which we had discussed in the last class. This constant term was refractive index. Refractive index we did know completely. Refractive index we had done?
Oh, yes, ma'am.
Yes? Okay. So I hope you are able to relate it. So N21 means this also I have told you refractive index of second medium with respect to the first one, that you can write it as N2 by N1 or N1 by N2 you can write. So their ratio remains constant and that constant term is your refractive index. This is known as Snell's law and it's a very important law. So this was missed. That's why I'm coming it back and telling you, because Snell's law is very important. Nobody is going to ask you Snell's law directly. Usually, Snell's law is not asked directly in the exams, but Snell's law application is there till the end of the lesson. We'll do prism, no, at the last. Till that time, also, you will be able to find Snell's law's application. So, carefully remember Snell's law application. And best way is what I have told you just now, before this, that take the refractive index of the medium, multiply it with sine I. Why? See, sine I by sine R is N2 by N1. Let's say this is N1, this is N2. What did I write? Sine I by sine R is N2 by N1, right? See, if you cross multiply it, N1 into sine I is equal to N2 into sine R. That's what I was telling you, know. Refractive index multiplied by angle sine of I. Refractive index multiplied by whatever is the angle, 30-degree, 40-degree, angle of incidence, angle of refraction. But remember, refracted angle of refraction or whatever angle is given will come along with that refractive index of that material only. So this, I think, is the best way to write, because sometimes it becomes confusing whether it was N2 by N1, N1 by N2. N1 is the medium where ray is incident, and N2 is the medium where ray is getting refracted. So these two were the laws of refraction that were very necessary. Note it down, then we'll do two cases. How much bending is allowed for a refracted ray? What will determine this angle of refraction? We'll do this. Just copy all these points because these points are essential for your examinations, subjective examinations. Done class. Now see how to determine how much refraction will occur. This is important for your ray diagrams. You have to draw no ray diagrams. From that it is important. See class. If your light ray travels from denser to rarer medium, denser medium is this. This is a rarer medium. If your light ray is traveling from denser to rarer medium, fine, denser to rarer. Denser, rarer, I have discussed. This means optically denser, not that density, optically denser. So what will happen over here? This is N1, this is N2. Apply Snell's law. So sin I by sin R can be written as N2 by N1. It's better if you write it N1 into sin I is equal to N2 into sin R. Now, when we say a medium is denser, that has a greater amount of refractive index. So if N1 is a denser medium, N1 will be greater than N2. Now, remember, always remember, it bends away from the normal. Now, how? First, look at this. N1 into sin I is equal to N2 into sin R, and N1 is greater than N2. It means N2 by N1 is less than 1. N1 is greater than N2. So N2 by N1 is less than 1. And what is N2 by N1? N2 by N1 is sin I by sin R. So this means sin I by sin R is less than 1. Sin I is less than sin R. I is less than R. It means this angle is now narrower and this angle is broader. So it means how do you determine away or towards normal? Check the path of incident ray. If it was not to get refracted. If this ray didn't get refracted, incident ray would have covered this path. So away from the normal means this. This is going away from the normal. Understood? This is going away from the normal. This is your normal. You are moving the ray away. Fine. So if your light travels from denser to rarer, why this is important? Because next topic that we'll do, a major big topic and a very important topic that we'll do will be total internal reflection. For that, you have to have this concept. Note it down, then we'll do the other case. If it is from rarer to denser. All right, copy down it quickly. And whenever you complete a portion, just text me in the chat box done. So I get an idea about who has written or who has not written. So accordingly that I start. Because now otherwise it becomes difficult because online I cannot peep into your notebooks and see how much you have written. So it's better whenever you complete, you can just text done. All have completed? Okay. Now, if the ray, no, if it travels from rarer to denser medium, it won't bend away from the normal. This will bend towards the normal. This means this is now your rarer, this is now your denser. That means N1, this is rarer. From rarer to denser medium, from rarer to the denser medium. So if this is denser, it means N2 is greater than N1, right? And what is the theory part says? The theory part says it bends towards the normal. It means this was the path of the ray that was to be traveled by the incident ray. If I move away like this is moving away from the normal. If I move like this is moving towards the normal. Again, angle of refraction will be this. This is moving towards the normal. This, please keep in mind how to draw it. Draw the actual path that was supposed to be covered by the incident ray, then away and towards, mark accordingly. See here. Now N1 into sin I is equal to N2 into sin R. That will remain here the same. But N2 is now greater than N because your rarer medium has changed and denser medium both have exchanged, right? So N2 by N1, this will be greater than 1. Agreed? N2 by N1 is now greater than 1. And N2 by N1 is what? Sin I by sin R. So this whole term is greater than 1. It means sin I is greater than sin R. Angle of incidence is greater than angle of refraction. Can you see this is angle of incidence and this is narrower angle of refraction. So this part no, that I have written in both the cases, this is the proof. So it can come in theory as well as in numericals also. Not numericals, it can come in derivation like proof that angle of incidence is greater. Or it can come in your conceptual questions like how can you show that, or with proof explain, or how can you show that, or what is the path of the ray of light when it travels from denser to rarer. So according to the marks, answer. If it's a marker of 2, let's say 2 marker, you have to show this at least. 1 marker, simply away or towards. Note it down, please. Just copy down this question. And try this. Whoever gets the answer, send me in the chat box. Then I'll discuss. See, class, ray of light passes through a plane boundary separating two media whose refractive indices are mu1 3/2 and 4/3 is the second refractive index. If ray of light travels from medium 1 to 2 at an angle of 30 degree, what is angle of refraction? Simple Snell's law. Mu1, I have told you already that sometimes n will be written, sometimes mu1 will be written. So here mu1 by mu2, that is n1 by n2 is equal to sin I by sin R. That you have to write. The same thing. See here, over here for the first part. If you write it as mu1 into sin I, because this is the first medium. Here the ray is incident. This is mu1, which is written as 3/2. And this is angle of refraction, which is written as 4/3. This is written. Fine. So mu1 into sin I is equal to mu2 into sin R. Mu1 is 3/2, mu2 is 4/3. I is given as 30 degrees. See, this is mentioned. Only this was unknown. So directly also you can write this, that sin I by sin R is mu2 by mu1. But sometimes, it becomes confusing whether it was 2/1, 1/2, which entered, which left. So that's why I say refractive index into sin I, refractive index into whatever is the angle. So when you solve this, you will get R as sine inverse 9/16. All right, note down the solution. Similarly, the same part has to be covered. Same, exact procedure. Here, what happened? Mu1 and mu2 are just exchanged. Why? Because now this is normal. Mu1, mu2, their values have exchanged in the sense ray is now traveling from the opposite medium. The solution is there. Quickly copy down the solution. Then I'll stop. Now, fresh topic. I'll start from the next class. So quickly copy down the solution and text me when all of you are done. I'll stop the class. Okay, class. All those who have done, you all can leave. Thank you so much, class.